What is fine-tuning? You ask an AI to write a legal contract. It sounds good, but it uses the wrong jurisdiction. You ask it to complete medical code. It invents drug names. The problem is not the model's intelligence. The problem is that a general-purpose model does not have your domain expertise baked in. Fine-tuning is the solution. Today on Neural Monk, we are going deep on fine-tuning, what it is, how it works at the technical level, the different methods engineers use, and when to use it versus alternatives like RAG. This is the most important technique for deploying AI in the real world. Let us start from the beginning. Before we can understand fine-tuning, we need to understand what comes before it. Pre-training is the first and most expensive phase of building a large language model. The model is exposed to a truly enormous amount of text. We are talking about trillions of words from books, websites, academic papers, code repositories, and more. Through this process, the model learns the structure of language, the facts about the world, how to reason through problems, and patterns in code. This training runs on thousands of GPUs for weeks or months. It costs millions of dollars. The result is called a base model, something like GPT, Llama, or Mistral. A base model is like a brilliant generalist who has read the entire internet. They know a lot about everything, but they have not yet been trained for your specific job. Pre-training is done once, by AI labs with massive resources. Fine-tuning is what you do with that base model. Now, what is fine-tuning? Here is the analogy I want you to remember. Imagine you hire a doctor who completed general medical school. They have deep knowledge of medicine, human biology, pharmacology, and clinical reasoning. That is the base model. Now you send them for a 2-year specialization in cardiology. They do not forget everything they learned in medical school. They build on top of it. They gain new, specialized skills while retaining their general foundation. That is exactly what fine-tuning does to a language model. We take a pre-trained base model. We continue training it, but this time on a small, targeted dataset specific to our task. The model keeps all its general language knowledge. It gains a new domain-specific skill. The pipeline is simple. Base model plus task data equals a fine-tuned model. This can be done with thousands of examples, not billions. It takes hours, not months. And the cost is a tiny fraction of pre-training. The result is an expert model, built for your exact use case. Should you fine-tune a model or train one from scratch? In almost every real-world case, the answer is fine-tune. Here is why. Training from scratch requires billions of tokens of training data. It takes weeks to months of compute time. It demands thousands of GPUs running in parallel. And it costs anywhere from $1 million to $10 million or more. Fine-tuning, by contrast, needs only thousands of targeted examples. It runs in hours to days on just 1 to 8 GPUs. And it might cost you $100, or a few thousand at most. The reason fine-tuning works so effectively is that the pre-trained model already knows language. It already understands how sentences work, what words mean, how to reason, and how to write code. You are not teaching it from zero. You are redirecting its existing capabilities toward your domain. In almost every real-world scenario, fine-tuning gives you 90% of the benefit of training from scratch at 1% of the cost. The only time you should train from scratch is when you are working with an entirely new modality or data type that no existing model was trained on. There are two main categories of fine-tuning, and understanding them is critical. The first is full fine-tuning. In full fine-tuning, every single parameter in the model is updated during training. This is the most powerful approach. The model can change substantially, but it requires enormous GPU memory. For a 7 billion parameter model, that means you need multiple high-end data center GPUs. And there is a risk called catastrophic forgetting. The model may lose some of its general knowledge as the new training overwrites previous patterns. The second category is parameter-efficient fine-tuning, or PFT. The insight behind PFT is this: when you fine-tune a model for a specific task, the actual weight changes are surprisingly small and low-dimensional. You do not need to update every parameter to achieve a great result. PFT methods freeze the original model weights and add small, trainable components. The most popular PFT technique is LoRa low-rank adaptation. Other methods include prefix tuning, adapter layers, and QLoRa. With PFT, you train less than 1% of the parameters and achieve results nearly identical to full fine-tuning. For most real-world projects, start with PFT. LoRa is the most widely used fine-tuning technique in the world today. Let me explain exactly how it works, mathematically. When you fine-tune a model on a specific task, the changes to the weight matrices turn out to be inherently low rank. That means they can be approximated very efficiently using too much smaller matrices. Here is the LoRa approach. Instead of modifying the original weight matrix W directly, LoRa freezes W completely. It then adds two small learnable matrices, A has shape D by R, and B has shape R by D. Where R is the rank, a small number, typically between 4 and 64. Only A and B are updated during training. At inference time, the new effective weight is W plus the product of A and B. This can even be merged into W after training, 0 overhead. Now for the numbers that make this remarkable. A full fine-tune of Llama 7 billion parameters updates all 7 billion weights. LoRa with rank 16 trains only 4.2 million parameters. That is 0.06% of the original model. This means you can fine-tune a 7 billion parameter model on a single consumer gaming GPU. That is the power of LoRa. Now let us look at how models like GPT-4 and Claude are actually fine-tuned. This is not a simple one-step process. It is a carefully engineered three-stage pipeline. Stage 1 is instruction fine-tuning, also called supervised fine-tuning or SFT. The model is trained on thousands of examples of instruction response pairs. Here is a question. Here is the ideal answer. Here is a task. Here is how to complete it. This teaches the model to follow instructions and produce structured, helpful responses. But SFT alone is not enough. A model trained only on SFT can still be sycophantic. It agrees with whatever the user says, even when the user is wrong. Stage 2 is training a reward model from human feedback. Human labellers are shown multiple model responses and asked to rank them. The reward model learns to predict which responses humans prefer. It scores outputs based on 3 dimensions: helpfulness, harmlessness, and honesty. Stage 3 is reinforcement learning using an algorithm called PPO. The main model is fine-tuned further to maximize the score from the reward model. Over thousands of training steps, the model learns to generate responses that are genuinely helpful, safe, and honest, not just fluent. This entire process is called reinforcement learning from human feedback, RLHF. It is the reason ChatGPT, Claude, and Gemini feel like assistants, not just text predictors. Fine-tuning is powerful, but it is not always the right tool. Sometimes you should use RAG, retrieval augmented generation, instead. Understanding the difference is crucial for building production AI systems. Here is the fundamental distinction. Fine-tuning changes how the model thinks. It modifies the model's weights, its behavior, its style, its domain reasoning patterns. The knowledge and skills are baked in permanently. RAG changes what the model knows at query time. It retrieves relevant documents from an external store and injects them into the prompt. The model's weights do not change, only the context it is given. So when do you use fine-tuning? Use fine-tuning when you need to change the model's style, tone, or domain logic. When you need it to always respond in a specific format. When the knowledge is static and well curated. When no amount of prompting gets you the behavior you need. Use RAG when you need live, frequently updated information. When your data changes every day or every week. When you need citations and verifiable sources. when hallucination reduction is the primary goal. The golden rule: if you need the model to think differently, fine-tune. If you need it to know something new, use RAG. And the best production AI systems do both: a fine-tuned model backed by a retrieval pipeline. Fine-tuning is not just an academic technique. It is running in production at scale today. Let me walk you through the real products built on fine-tuning. GitHub Copilot, arguably the most successful AI product in software, is built on a code completion model fine-tuned on hundreds of millions of lines of open-source code. It does not just know Python. It knows patterns, idioms, common mistakes, and library APIs. Bloomberg GPT is a language model fine-tuned on financial text, earnings transcripts, analyst reports, regulatory filings. It understands finance the way a domain expert does. MedPLM is Google's medical AI, fine-tuned on clinical notes, medical literature, and diagnostic guidelines. It can answer medical licensing exam questions at expert level. In legal technology, models fine-tuned on contracts and case law are reviewing documents and flagging compliance issues faster than teams of junior lawyers. Customer service bots fine-tuned on company-specific question and answer data handle support queries with accuracy that generic models cannot match. And educational AI tutors fine-tuned on pedagogical frameworks adapt their explanations to each student's level in real time. The pattern is identical every time. Take a powerful base model. Give it high-quality domain data. Get a production-grade expert AI. The domain is unlimited. The approach is proven. You now understand fine-tuning, from the mathematical foundations to production deployment. Let me bring the complete picture together. Pre-training creates a general expert base model trained on trillions of tokens at enormous cost. Fine-tuning continues that training on a small, targeted dataset, keeping all general knowledge and adding a new domain-specific skill. Fine-tuning delivers 90% of the benefit of training from scratch at 1% of the cost, in a fraction of the time. Full fine-tuning updates all parameters, powerful but expensive. LoRa and PFT update only 0.06% of parameters with nearly identical results. Instruction fine-tuning teaches models to follow instructions precisely. RLHF, combining SFT, reward model training, and PPO, produces aligned AI that is helpful, honest, and safe. When you need to change behavior, fine-tune. When you need fresh knowledge, use RAG. When you need maximum production quality, combine both. Fine-tuning is the engine behind every major AI product you use today. GPT-4, Claude, GitHub Copilot, MedPLM, and Bloomberg GPT. If this video helped you understand fine-tuning, the next one in our All About LLM series covers building a complete RAG pipeline from scratch. Subscribe to Neural Monk so you do not miss it. See you in the next video.